So for the next talk, in the black belt track, we are going to have Mr. Brendan Gregg, who is, I would say, a performance expert among other things. When I have performance problems, since I'm barely running anything myself in production, I usually look at top and I'm like, something seems to be happening. Just let's reboot the machine or restart the container or something like that. But when you run 1/3 of the US internet traffic, so you might be wondering who's running 1/3 of the internet US traffic. I'm gonna give you a hint with the color of Brendan's shirt. And if the hint is not enough, I'm gonna tell you that it's Netflix. So when you run Netflix, you're not gonna run top and reboot random machines to get more performance out of your servers. You need way better than that, and that's what Brendan is going to talk about.
G'day, my name is Brendan. I work at Netflix. Thanks, Jerome, for the introduction. And I'm going to show you how to, So I'm going to show you how to identify bottlenecks in a container environment. So whether it's in the host or container, using system metrics, using flame graphs to understand application code in a container environment, and deeper in the kernel using tracing tools. I'm going to focus on how this works on Linux using 4.9, a recent version of Linux. I'll include some Docker specifics, and I'll start with a summary of how we do this on Netflix, which is Titus. We're using containers at Netflix because it helps developer velocity, it helps manage dependencies, and it helps with the cycle of development. Titus is our cloud runtime platform for container jobs. It manages scheduling and also container execution. That is where it will talk to the AWS EC2 API and also the Netflix API and manage things appropriately for our environment. There was a blog post posted just yesterday on the Netflix tech blog that goes through this in depth from the Titus team, which I recommend reading. The current Titus scale at Netflix, we're at the scale where we're deploying over 1 million containers per week. And that's on over 2,500 instances, and they're fairly large EC2 instances. The use cases for Titus include services. These are long-running services that include stream processing, UI, Node.js, and internal dashboards. Then there's batch jobs, which are more short to long-term, algorithm training, reporting, and there's also media encoding as a queued worker model. Container performance at Netflix, well, the way it's set up with EC2 and instances, we can scale them up when we need to, very easily. Amazon makes that very easy to scale up. And also with Titus, we can balance out the workload when needed as well. So the architecture that we have already solves a lot of performance problems. Some of the things that we then need to do include primarily application analysis. So we've moved applications to containers. How are they running? Can we still analyze them? Host tuning, container analysis and tuning, C groups, and capacity planning to reduce over provisioning. To get really good at this, we need to understand containers well, which I'm sure most of us do. And so I'll go through this quickly. Containers are built up of namespaces. Namespaces restrict visibility, so there are several namespaces in the kernel. And I've drawn a diagram of the process ID namespace. So if you're in the process ID namespace, you can only see processes that belong to you. They also get mapped differently. So process ID 1 might be something else in the host. As a performance engineer, we need to know this because if a container user says they have a problem with the process ID, it's going to look different in the host. Control groups, well, namespaces restrict what you can see and control groups restrict what you can use. And there's several control groups as well. Some of these have been around for a long time. I've drawn them as different shapes because control groups give you more flexibility and more fine-tuned resource control versus the physical resources. So for CPUs, I may say this container gets 1.5 CPUs. I may also have a more flexible model that varies over time. And that's why I've drawn these as different shapes. So the combination of namespaces and control groups is what we call a container. With cgroup version 1, some of the key groups included the CPU cgroup, which is now CPU and CPU accounting, that has the caps for CPU usage. And so in Docker 1.13, we can now set that up. CPU shares for something more flexible and usage statistics. Memory has the limits, including kernel memory and out-of-memory killer. And block I/O has weights, IOPS, and throughput caps as well. CPU shares is often described as complicated. I think the algorithms that are used are not that complicated. So the container CPU limit that you get is your container share value divided by the busy shares on the system. So if I had 100 shares and there were 200 busy shares on the system, I would get 50% of the available CPU. If I had 100 shares and there was 100 shares that was busy on the system, I was the only container that was busy, then I get all of the CPUs. So this is a way that I can use other tenants' idle CPU proportionally. Another way to think about this is what is the minimum guaranteed CPU that you might get? And that would be your container shares divided by the total allocated shares. That's worst case. That's when every container is busy. Where I think this gets tricky is what if another tenant moves in? What if another tenant who's been there for a while now consumes more CPU? Your available CPU for a tenant can decrease. And you might be thinking that it's a problem with your own code, you've just pushed a change, but it's something external to that container. So this can make analysis tricky. Why did performance regress? Was there less bursting available? We call using the CPU beyond that minimum bursting. cgroup version 2, there's been a major rewrite that's been happening for a while. Some of it's in the kernel, some of it isn't yet, the CPU cgroup version 2 code. It supports nested groups, it has a better organization and consistency. And if you see any docs or talks by Tejun Hao from Facebook, he explains it pretty well. And the other basic component of containers we need to understand well is the container operating system configuration. So what file systems are we based on? Have we layered file systems? Are we on overlay on top of ZFS? On docker.com, there's actually some really good documentation in the in practice pages for each of the file systems, which summarizes that well. Networking, of course, can be notorious depending on how you set it up, whether you're using bridge, host, or overlay networks, as overlay networks can come with a performance cost. So again, fundamentals about understanding what it is we're analyzing. Given that, how do we analyze it? There's 4 things to understand about performance analysis. First, there's one kernel. That can simplify some things. So one kernel to where I can compare all the metrics between the containers. There's 2 perspectives, whether I'm looking at it from the host or whether I'm looking at it from a container guest. And there's namespaces and cgroups, which are summarized very quickly. You can apply different methodologies to understand what containers are doing. So my use methodology, workload characterization, checklists, and event tracing. And you'll see some examples of this in my talk. So the use method, I came up with this a while ago. It's proven very effective in production. And it is where you take a functional diagram of the system, and for every resource you only want 3 metrics: utilization, saturation, and errors. A problem we can have in performance is there's too many metrics. I run netstat -s and it goes past the screen. This lets you focus on the key critical metrics for understanding performance, and it also poses questions for the system for you to answer. So the metrics the operating system may provide you can be incomplete, even though there's so many of them. The use methodology, by posing questions first, will then show where you've got blind spots and where those metrics aren't readily available. You need to do some more work. As an example for physical CPUs, that's pretty simple. Utilization is time busy. Saturation would be run queue length or latency. Latency is even better. Errors could be ECC errors you get from CPUs. You can apply this methodology to C groups as well, and think of C groups as a software resource. So if I was to apply this to the CPU physical cap C group, or that configuration, utilization is the percent that you've used for that cap. So if I'm capped at 2 CPUs and I'm using one of them, I'm at 50%. Saturation for the CPU caps. Well, fortunately, there's a metric in the kernel for this that tells you the number of times you've been throttled because of that cap. So we have a saturation metric. Errors may not make sense, so it depends on the resource. These pose questions, they may not be good questions. And you can do this exercise for, say, shares as well. How would you measure utilization? Well, now it gets really more complicated. What does utilization mean when your CPU availability changes because of shares? You might like to pose that in terms of the minimum guaranteed utilization. That way you can tell when you're bursting because you're running at over 100%. Saturation, how would you measure that with shares? Well, I'd measure it if I was getting blocked and I had run queue latency because I'm waiting on my turn on CPU because other tenants were busy. So you can see you can go through all of the C groups, and the C groups may change quite a bit with version 2, but come up with metrics that make sense. Now getting into some of the more specific tools, the first section I've got is host tools, and some of the challenges we have here include the process IDs in the host don't match those seen in containers. Symbol files aren't where tools expect to see them, and the kernel currently doesn't have a container ID. I'm going to go through some CLI tools. You may look at these and say, we're never going to use CLI tools. We have GUIs and dashboards and they're much, much better, and that's fine. The GUIs and dashboards source the same metrics that the CLI tools use. By showing you the CLI tools instead of, say, Netflix's specific dashboards, I'm showing you a more common denominator on Linux. I've done container performance analysis at Netflix for a while, and the truth is most of the issues, this is especially the case when you're deploying new technology and people don't know why things are going wrong and they'll tend to blame the new technology, blame the unknown. But most of the time it's actually just the operating system and just the physical resources that are causing performance issues. And so my job for a while has been to exonerate containers and say, no, containers are not the problem, it's operating system virtualization, it's just partitioning the threads, it doesn't actually matter. And my standard methodologies found some of the key problems. So I'll go through that very quickly just as a refresher of basics, but I wanted to put it first because, to be honest, this will solve a lot of problems on container environments because the problems aren't specific to containers. I have a diagram which I've shared online which goes through all the performance tools I use for understanding Linux. It's not as bad as it looks. It's actually maybe it is a bit as bad as it looks. To make sense of that, I then have methodologies. So one methodology, very simple, is a host performance analysis in 60 seconds. And I've shared this on the Netflix Tech blog. This is the first 10 commands I would run if I'm told, this system has an issue. What should I go through and what should I look at? I used this only a few days ago within Netflix as someone had a suspected issue, had no idea where to start. It's like, well, here's a starting point, just try this, and quite often that will find them. To get more detailed, there's host resource, examining host resources with the use method, and that's where you list out all the resources. Again, I've shared all of this online. And it's not just CPU, memory capacity, storage IO, network, there's also buses and other resources. And then you try and figure out what utilization, saturation, and errors would be for each of those. Again, the point of this methodology is to give you better visibility and fewer more important metrics so you can solve problems more quickly and you don't have blind spots. If you're looking at this thinking, oh, I'm never going to run all those commands, that's fine. Have it in a GUI. Have a dashboard that does the use method for your system and lists all of those metrics. Then for host-based analysis, drilling down further, there's my IOSnoop tool, which I published first on Linux in my perf tools collection, but also more recently in BCC BPF as BioSnoop. And that it's like TCP dump for disks, so I can see latency of individual disk I/O. But to be honest, I don't like to use I/O Snoop first because it can be more effective to look at performance from the application when the application talks to the disks. That's where the application will block and wait for storage I/O. And so tools like ZFS slower, and I've got Btrfs slower and ext4 slower, I can say, show me I/O that was slower than 1 millisecond, and then it lists them out so I can focus on it. I actually ran this from our production Titan system that's running Docker. So if a container user on that production Titan system said, we're being throttled by disks, we've got all these outliers, it must be disk I/O, I can run this and say, well, I don't really see, I mean, if you look at the timestamp column, we're not getting slow disk I/O that frequently, and that spans like a minute, and there hasn't been that much. So this is great for exonerating the entire storage subsystem, because it's not just disk I/O that can make things slow, it's also locks in the file system and allocations and so on. Latency histograms, and I've got tools for this as well. So Btrfs distribution is also ZFS distribution. I mean, it's pretty early to be waking people up. I'm only 15 minutes in. I mean, I didn't think I was that boring. So these tools, I like these as well because I can more quickly identify multimodal distributions, exponential latency. So this is another example from our production container system. It's running on flash disks. This is a test system. We're testing out Btrfs, and you can see there's another mode of latency which I would assume would be cache misses. I can drill down further. So useful as well. So that's just a very quick look at some host tools. Now for when we're on the host and we want to look at containers, the first thing I like to understand is namespaces. So one of the features of how Linux does containers is that it can be configured differently. And so namespaces aren't, you could share namespaces between containers, they aren't necessarily unique. I wrote a very simple bash script called docker ps ns, which lists the containers, the main process ID for the container, and then lists all of the namespaces, and then I color in red if the namespace is shared with the host. I filed this as a ticket, someone's going to add it to docker ps, so you can easily get this. Now that's just a starting point, so I understand the namespace configuration. Then there's tools for looking at host resource usage in the context of containers. So there's systemd cgroup top, so I can look at particular cgroups and its CPU and memory usage. I really like Docker stats. That's a great high-level summary. It should be called Docker top instead of Docker stats, but that's okay. And so this, again, is a screenshot from a production Netflix container system, and you can see a lot of containers are quite CPU busy. And this is useful as well because I can apply a few different methodologies. I can apply I can look at resource utilization from the use method, so I can see how much CPU it's using, memory usage versus its limit. I can also do some workload characterization. So if it's working, I can look at the network I/O and block I/O and how much memory it's using to characterize that. Running top from the host currently is not that useful. It doesn't have a column for a container ID. And the kernel doesn't really have a container ID yet. Although there's been some discussions about what can we use as a container ID. Can we use the cgroup inode? It can be useful because once you're given a hot process ID, you can then figure out what that belongs to. htop did add a cgroup field, and unfortunately, when I ran it, it's not working here because it's truncating the actual Docker container name. We could fix that, but then that becomes very Docker specific, like how it's using cgroups. It's also specific to cgroup version 1, which will change with cgroup version 2. Each time I look at these, it's like we really need a container ID in the kernel to make this simple. Now I had a hot process in those two screenshots. Who does it belong to? There's lots of different ways you can do this. You may have a better way than I do, but I can grep out of the sysfs cgroup files and quickly see the Docker container that process ID belongs to. Some Linux commands that aren't Docker specific, I can look in its namespace directory under proc. I can look at cgroups as well and then map it back to the container that way. Namespace enter is a great command, and for performance engineers, you need to get good at this. Given that process ID, I can use it to identify the host name, so I could say, run the host name in the UTS namespace for that process ID, and then it's told me the container host name that it's on. And I've made a short list of some handy one-liners for nsenter, so I can go into the network namespace and run container netstat, I can look at container file system usage and so on. And container top. So given that process ID, I can go and run top in that namespace and see that that's actually Java, process ID 301. And in more recent kernels, the mapping is in proc status. So you can see the namespace process ID. CPU profiling. Perf is a great profiler. It's the standard profiler and tracer for Linux. And you can run it many, many different ways. Here I'm running perf record, 49 hertz, all CPUs, cold graphs, stack traces. You can aim it at a process ID, you can aim it at a C group if that works. But if you try this in a container environment, there are some problems. In fact, this is probably where I've spent more time working on containers than anywhere else, as containers operating system virtualization, we don't have a lot of different kernel code that's running. If you're already running C groups, whether you're using containers or not. So in our container environments, we don't have a lot of system time or kernel time for me to investigate. If you looked at the user to system ratio in our container environment, it's mostly user time. It's mostly the applications we're running in containers. And so the biggest wins for a performance engineer like me is not really to dig into the kernel, but it's actually to dig into the applications. And one of the most effective tools we have at Netflix for that is doing flame graphs. And so we do them for Java, we do them for Node.js. Flame graphs are built upon the profiles that perf can collect. But if you run it on a container environment, here's a couple of problems. If you run perf script, it's saying that it couldn't find libc, which seems odd, and it couldn't find this map file, which in that case would be for Java symbol translation. The problem is I'm running perf from the host, and that libc is in a different mount namespace. It exists in the container, but not the host. And for the second one, there's two problems. The map file exists in the container, not the hosts /temp, and also the process ID is different. So I've profiled it in the host where that's called process ID 28321, but in the container, that's called process ID 301. So if I looked in the container, I would find a temp perf-301.map file. Now we can work around this. So we can copy those files into the host when we use perf so that we get symbol translation, we can do flame graphs. And Alice Goldfuss did a great blog post about that and went through the steps. We could also run nsenter on perf. We can, or we should, also just fix perf. We have this problem in BCC as well, which is the advanced tracer, and we just fixed BCC. So we got BCC to, when it's run from the host, it understands namespaces, and it understands where it should be looking for map files, and where it should be looking for these symbol files. We kind of should fix this in perf. I think part of the problem with why we haven't fixed it in perf yet is the problem of having workarounds. We have a workaround. We can copy them around. Perf is under massive development in Linux. People are fixing things all the time. And if you go to the perf mailing list and say, I've got a problem, there's no way we can do this, it gets fixed really quickly. But if you say, here's a problem, oh, we have a workaround, then suddenly it's not the top of the list of priority. So it's kind of annoying. We should fix it. Even though we have a workaround, we should actually fix perf. Once you have it fixed, you can create flame graphs, and the steps are pretty simple. I've got an example of flame graph in the background here. This one's missing Java stacks because I didn't run Java with preserved frame pointer. But I'm showing how much of that flame graph is in the kernel. So the kernel is these orange towers. And if I was to do, say, container overhead analysis, what's the overhead of running containers? I would be clicking to zoom into those kernel towers, and I'd be looking for things like, how much time are we spending in C group throttles? We've got an extra file system layer, so how much time are we spending on that? Networking, have we configured that in an odd way, and how much extra time are we? but it's not going to add up to very much. In fact, I had a look at this and I couldn't even find 0.1% overhead for the container configuration that we're using. Another source of metrics, if you're doing container analysis from the host, is cgroups. And so my example here is I'm looking at the CPU C group, and there's CPU stat, which has throttle time. So that's great for understanding if the throttle time is how much I've been throttled by the, say, a hard limit for CPUs. There's also NR throttled for the number of times I've been throttled. These metrics should be shown in performance monitoring GUIs, and we're doing that at Netflix. So Netflix Atlas is our cloud-wide monitoring tool. It's open source, and it fetches the cgroup metrics via Intel Snap. Netflix Vector is a per instance monitoring tool we have. This is different in that it's on demand, so it doesn't save historical data, but it also has a higher resolution, so it will show per second metrics. And we've enhanced that so that it can do per container breakdowns when you point it at a host. I wanted to mention Intel Snap because Intel Snap already has a Docker plugin for pulling out the cgroup metrics, and that's a metric collector. There's a plugin for collectd as well, so depending on which one you're using. So we have all these metrics. Let's see if we can make sense of them. So let's play a game, host or container or neither. Here's the scenario. A container user says they have a CPU performance issue. The container has a CPU cap and it has CPU shares configured. You notice there's idle CPU on the host. Other tenants are CPU busy. The throttle time is increasing from CPU stat. The non-voluntary context switches is increasing. And the container CPU usage equals its cap. So I've capped it at 200% and it's eating 200%. Although I've said that's not really a clue. And it's not really a clue because if I cap a container to 2 CPUs and it's eating 2 CPUs, it sounds like it's hitting its cap, but it could just have 2 hot CPU threads. And if you experimentally increase the cap, it wouldn't consume any more CPU because it can't. It's just got 2 threads that are on CPU. So that's not really a clue. It's kind of a clue. So going through this, hands up if you think this is capped by CPU shares. Okay, no one. Hands up if you think this isn't capped. The evidence there shows that the container isn't capped at all. Okay, I've got one person. Hands up if you think it's capped based on the CPU cap, the actual hard CPU cap. Okay, I've got a couple of people. Hands up if you think it's just capped by physical CPUs. Okay, now I've got a lot of people. Right. It's not capped by physical CPUs, we've got idle CPU on the host. But it is complicated because there's 4 different scenarios that this could be. In the slides I have a couple more of these games, and I've put the slides on SlideShare already. And trying to explain this to other people, I realized I needed a new methodology, so I've temporarily called it reverse diagnosis. Let's enumerate the possible outcomes, which is we're either physical CPU throttled, or we are cap throttled, or we are throttled on shares, asterisk. If you're throttled on shares, you're throttled on the physical CPU as well. Or you're not throttled, which can be a scenario as well. Once you understand those outcomes, you can then work backwards, like what metrics do I need to positively identify those outcomes? And you can do this methodology for the other C groups as well. I've drawn a nice flowchart for CPU bottleneck identification. So, is throttle time increasing? I mean, what I've tried to do is at the top of the flowchart, put the easiest things to identify first. So if throttle time is increasing, that only gets increased if we're cap throttled. So let's take that off the operating table to start with. And then we can go down, are we getting non-voluntary context switches? Well, if we're not, then we're probably not throttled, if we're not getting kicked off CPU. Do we have idle CPU? And right at the bottom, if other tenants are idle or not, it can help us identify whether we're share throttled or physical CPU throttled. We may be physical CPU throttled if your container is the only container on the system and you're trying to use more CPU resources than there are. Even though you've got shares configured, you're actually bottlenecked by the host's CPUs. Guest tools and container awareness. So some resource metrics are for the container and some for the host. This gets quite confusing if you're doing performance tools from the guest. And another problem doing performance tools from the guest is that you might lack system capabilities to run profilers and traces. You may know some of this quite well. So with CPU, we can see the host's CPU devices when you're logged into a container, but you can only see your own processes. So that can be a bit confusing. So this container has a high load average, but I'm not running anything. Memory, I can see host's memory. So this says I've got 8 gigs free, but if I try to consume 2 gigs, I get killed. That's because this container actually has a cap. Disks is confusing. I can run IOStat and see host disk I/O, but I don't have any container processes doing disk I/O on the container. Networking at least works. So with networking, if I try and look at TCP and device metrics, I just see my container. We could fix this by adding a metrics namespace, for example. And that might help with applications too. If you saw the Java talk yesterday, it was covered how Java can get confused about trying to eat 25% of visible memory, yet the container has a cap, so Java ends up being killed. A metrics namespace, if you do add a metrics namespace so that the container just sees its resources, I would consider adding a proc host stat and a proc host disk stats so that we can continue to use the host-based metrics for exonerating the host. I've used the host-based metrics, it's pretty cool because I can see whether there are noisy neighbors and other tenants making that container busy if you've only got access to the container. So it'd be nice to preserve that, make that optional. Running perf from within the container, that's complicated, even much more complicated than running it from the host. It initially doesn't work, but at least it gives you a helpful message. If you do some debugging, there's lots of different ways to debug containers. I just ran strace from the host. It shows that the perf event open syscall is blocked, and that's listed on docker.com as significant syscalls blocked by the default profile. So there's ways you can fix it, and I've got that in the slides. At the moment, one of the problems is if you ultimately fix all of this and you say, yes, I can run perf from the container, you do so and then you can see everyone. You're profiling all the CPUs. You don't have their symbol information, but it's like, what? I can see other containers. This is not right. And that's because at the moment the kernel, the perf subsystem is not container aware. There is a patch that was sent out January this year so that if you run perf from within a container, it only sees the container's tasks. So until that's integrated, this is pretty problematic, getting perf to work from the container. I would just run perf from the host. And there's lots of ways you could set that up. At Netflix we have Vector, and so developers can go to Vector and then issue a flame graph request and get a flame graph. The last section is tracing. And tracing is where you can get advanced information out from the system. There are 3 built-in traces to Linux, which I tend to focus on. There's ftrace, which has been around for a long time. Does anyone use ftrace? Got like 3 people? It's pretty cool. It's kind of a hacker's best friend. You have to like echo things to /syskernel debug tracing, or you can use my front-end wrappers perf tools. Perf events, which is great for profiling and PMC analysis, a kind of front end that we use for that all the time is CPU flame graphs, because we're using perf to get stack samples. And then eBPF, which is new, and that uses enhanced Berkeley packet filter. Berkeley packet filter is this weird technology in the kernel that if you run TCP dump this host and this port, that gets compiled into bytecode for efficiency and the kernel executes it. It executes it in a virtual machine in the kernel. And so some developers, or Lexis Territorio, have realized that we could take that virtual machine, we can enhance it and do lots more things with it in the kernel. And so one of the many things is we're enhancing it to do container performance analysis. If you saw the talk yesterday by Thomas Graf about Cilium, he's using BPF for doing container security and observability as well. So BCC, I'll get to in a moment, just to give you an idea of what ftrace looks like. This is using my func count tool from PerfTools, where in this example, I'm counting overlay file system function calls. So it's using kernel dynamic tracing, kprobes. Actually, it's actually using its own efficient version. It's not using kprobes, it's using ftrace for function counting, which is specialized and faster. All of these are potential points for further analysis. So I could look at, say, OVL fill merge, and I could say, kprobe that, okay, this time I'm using kprobe, and show me the stack backtrace and show me the arguments. So you can imagine using those two tools for a lot of kernel explorations. But there are some things ftrace doesn't do. Particularly, it's not good for doing advanced custom summaries in the kernel. And that's what BPF can do, where BPF can summarize via maps and give us summary statistics. And I've got a diagram of the internals. A great use case of that is doing histograms in the kernel. In this example, I'm looking at run queue latency of a process, and I'm doing it for 10 seconds. And it's showing me that most of the time the run queue latency is very low. This is an app in a Docker container. If I add other tenants so that it becomes CPU share throttled, I can now see that run queue latency, I've got this 8 to 65 millisecond delays. BPF is actually a really good tool for this, because the way it summarizes in kernel, we are not dumping every scheduler event out to user space and then post-processing. What I'm actually doing is, if you look at the count column and you think of that as an array, it's just populating that array in kernel. And then once a second, or whenever the program ends, it copies that array, which is what, 15 integers to user space, and then prints it out. So it's really, really efficient to do this. Although scheduler events are also really, really frequent. So you do have to pay some attention when you're doing scheduler tracing, because they can add up. A feature I added to this yesterday was doing run queue latency for getting it to do a breakdown for each PID namespace. So now I can see that process ID namespace, that's its run queue latency. The second one I see it's getting throttled. So I've got some 16 to 63 millisecond latency events. In the slides I do mention, we have a lot of BCC BPF tools for doing deep kernel analysis. We have not done much container IDs in them, partly because the kernel doesn't have a container ID. It's not that difficult to add, say, namespace information to the tools. And so, for example, I can dig out the process ID namespace from the task struct like this. I can throw that in the tools. And we have lots of tools we can enhance. So there's my diagram of the BCC BPF tools so far. I read a lot of these. And you can look at file system, latency, networking, scheduler, memory, lots of system calls, lots and lots of things. You can also go into the applications, and the last thing I want to mention is you might want to do analysis of Docker itself. And there are many different ways we can already analyze Docker. The pros and cons for BCC and BPF is it can trace both user and kernel events. So you can get context from both worlds. So as an example here, I'm using func count, and this time it's using uprobes to look at all the calls from Docker-D that contain Docker and get. And so it's able to tell me these fired while I was tracing. And there's 35,000 different functions I can trace from Docker-D to start with. So I can write some sophisticated tools, if I need to drill into Docker internals. I can print out stack traces for events, like I do here, stack count, when we're doing IAUtils get buffer. I also figured out how to do function arguments, and I wrote a blog post on it because it uses plan 9 depending on the compiler. And with some work you can get latency as well. So BPF, it can drill into the Docker internals as well as the kernel internals as you need to. So in summary, there's 3 main bottlenecks that I'd like you to be able to solve. One is whether you're bottlenecked on the host resources or the container. And so I had an example of using the use method and also a flowchart for looking at cgroup metrics versus host metrics. Digging into application code. Anyone already using CPU flame graphs for something? Oh, that's good. Now we have more than a dozen people. So CPU flame graphs are great because they will let you put your finger on which functions are slow. We use them at Netflix all the time. There are some challenges to do them in containers, but then they can be solved. And then when you want to go deeper in the kernel, you can use the tracing tools. These slides are on SlideShare, and there's also a tech blog about Titus if you want to learn more about containers. And some of the Titus team are here at DockerCon today, like Andrew Spiker, sitting down at the front. So please talk to us about containers at Netflix. We're also hiring, and I can recommend Netflix. It's a great place to work. But that's my talk, and thank you very much. So I'll try to answer a couple of questions and two quick questions.
Yeah, we can take like 2 quick questions. Thanks a lot, Brendan, in particular, for not being surprised by the light show. I think in my case, if there was a light show, I would like... I can't...
I noticed on your slide that you didn't have systat mentioned. I'm not sorry, not systat. System tap mentioned. The dynamic kernel module. Is that not? Is it just something that you're not? Not one of your ones that you like?
So system tap quickly. System tap's not in kernel. It's a good technology. It's done a lot of work. There's a project right now to make system tap BPF, use BPF as a backend. Once that happens, I'd feel safer about running it. So at the moment, we're getting the job done using the built-in technologies, which is ftrace, perf events, and BPF. I'd love to see system tap be a front end to BPF because they've done a lot of work with tap sets. Once they do that, I'll probably be using it more. But if you asked me several years ago, system tap was the only way to do some of these things.
All right, thanks everyone.